Hey everybody, Dr. White here with just a few more selected solutions from the Chapter 1 homework. This will be in addition to any that we have already talked about in class or will talk about in class. So first of all, number 10 from section 1.1 was to prove the formula for the union of three arbitrary events. So you want to prove probability of A union B union C is this stuff down here. And I'm going to do that in a series of set inequalities where if a step needs a special amount of explanation or justification, such explanation will occur here in the sidebar. So starting with this, I am going to treat B union C as one set by itself as opposed to this other set, A. So now I'm looking at the union of two sets. But we have theorem 1.1 number 5 in the book already proved that says that the union of two sets is the probability of the union of two sets is the sum of their probabilities minus the probability of their intersection. I'm just going to apply that where the A in the theorem is the A in my situation, and the B in the theorem is the B union C in my situation, thus getting this. Now I'm going to focus on probability of B union C and apply theorem 115 again, writing it like that. Then I'm going to focus in on probability of A intersect the B union C. And there is a distributive law that says A intersect B union C is A intersect B unioned up, with A intersect C. Those are the same sets, therefore the same events, therefore they have the same probability. So all I've done to get this step is to replace this expression with this expression that it's equal to. Staring at that expression, I see that once again it is the union of two sets. And so I apply theorem 115 again to it. Everything in the square brackets here is just theorem 115 applied to this expression. So that's the only change that I've made from this step to this step. Again, notice the explanations for the step off to the side. Continuing on in my chain of equalities, I can gather together all of the minus probability of the intersection of three sets. This is a commutativity of addition type of thing. And having worked the minus sign through, I've got minus minus on that last probability is a plus. And this is what I wanted to prove. So that was just arithmetic property. So you'll notice there's no particular explanation for that step over in the sidebar. That's one way to do a proof for theorems of this sort is if you've got to prove an equality, start with one side and step by step transform it into the other side of the equality, but justify the more intricate of your steps with explanations in some easy to find place like a sidebar. Go slow when you do this, and be generous in how much words and citation you use so that people can see exactly why you're taking each step. That's how you do a proof. Okay, the next one was problem number 8 from section 1.2. And this is where you're making a pizza and you can choose from any of 3 sizes, any of 3 types of crust, and you can also choose 0 to 12. There's like 12 different toppings available, and you can choose any number of them, like all the way from none to all 12 of them. And I say that the number of ways to build your pizza would be 3 times 3 times 2 to the 12 using the multiplication principle. How do I get the 2 to the 12? Some people saw that, and some people had more complex expressions there, which were correct, but but let's see why the simple one here is correct as well. Well, the reason is you can choose any number of toppings from 0 to 12. And so if you got a set of 12 toppings there, then when you're choosing some of them, you're choosing a subset of them. But how many subsets are there for a set of size, let us say, n? There are 2 to the n subsets for a set of size n. Well, why is that? Well, one way to see this is to set up a job for yourself. The job of picking a subset out of a set whose size is n. You could break that job into a sequence of n tasks, one for each item in the set. Your first task is to decide whether or not to pick item 1 in the set to be in your subset. There are 2 ways to complete this task. You could decide to take it. You could decide not to take it. 2 ways. Independently of that, there are 2 ways to decide whether or not to pick item 2 to be in your subset, and so on until you see that there's 2 ways to decide whether or not to pick item n to be in your subset. That's n 2's multiplied together for a product of 2 to the n. And so you could say 2 to the 12 up, here. There's another way to see that. We could think the number of subsets of size n, if we need to count that up, we could think in terms of cases. There are actually 13 cases. First case is that the subset has no elements. It's the empty set. Second case is that it has 1 element. Third case is that it has 2 elements, all the way up to the case where it has 12 elements. That's 13 total cases. And if you can find the number of subsets of each of those sizes, if you can find the number of ways, then for each of those cases, then you can add them together. And so with that analysis, the number of subsets of a set that has size n would be the sum, k goes from 0 to n, for the number of subsets of size k out of that set of size n. Okay? But we know that the combinations of n things taken at a time equals the number of subsets of a set of size k out of a set of size n. Furthermore, by number 12 in this section that you had to prove, one of the equalities you had to prove was that this equals this, and you did it with the binomial theorem. And so here's another way to prove that the number of subsets of a set of size n is 2 to the n. Great. So you don't have to offer up those proofs because they're in other problems. They're mentioned in the book, all this kind of stuff. But you certainly do need, to do an analysis like this to solve your problem. How about number 16, also from section 1.2? So this is the one where there's a bunch of little candy hearts. There's 52 of them, and they're in a bag, I guess. And you're gonna pull 9 of them out at random without replacement. And there are all these different colors to the hearts, 19 of them are white. And then there's a certain number that are tan and a certain number that are yellow and so on. And you first, in part A, wanted the probability that 3 of them are white. Well, by the equal likelihood principle, since all samples of size 9 are equally likely, because you're drawing randomly, you could just count the number of ways to pick 9 hearts where 3 of them are white and 6 of them are non-white. And then after you've counted that, count up the number of ways to just pick any 9 hearts and divide. And so you're You're doing the number of things in the event divided by the number of things in the sample space, and you're getting the probability. Well, for the top, you should probably split the job of picking 3 whites and 6 non-whites into 2 tasks. Pick your 3 whites, pick your 6 non-whites. Now, there are 19 whites available to pick your 3 from, so there's this many ways to do that task. There are the rest of the hearts, and that's 33 of them, 52 minus 19, that are not white, and you have 6 that you need to pick from there. 33, choose 6. So that product is the top number. And the number of ways to pick 9 things from 52 things is 52, choose 9. So there is a way to express your answer for part A. For part B, what's the probability you pick 3 whites, 2 tans, 1 pink, 1 yellow, 2 green? Same idea. But for the top, you're looking at the number of ways to get that kind of color arrangement somewhere in your sample. So you look for the number of ways to pick your 3 whites, the number of ways to pick your 2 tans, and there's 10 total tans to pick from. There's 7 pink things, you got to pick 1 out of them. There's 5 yellows, you got to pick 1 out of them. And there's 6 greens, you got to pick 2 out of them. There's some other colors there, but you're not picking from them, so you don't have to include anything about them in your sequence of tasks that completes this job. Same kind of denominator. I note some people offered up an answer like this to part B, where they're saying, all right, there's a 19 over 52 chance to pick a heart on your first draw. I'm sorry, to pick a white on your first draw. And then on your second draw, there's only 18 whites left and there's 51 hearts left. So 18 over 51 would be the chance of getting a white on your second draw, given that you've got 1 on the first draw. And then 17 over 50 is the chance of getting a white on your third draw, given that you got whites on your first 2 draws. And then you head into the greens and say, all right, on my fourth draw, chance of a green, given that I haven't drawn a green yet, will be the 10 that are still left. I'm sorry, tan. We're looking at tan. On the fourth draw, haven't drawn any tans yet, so there's 10 still left in the bag, but there's only 49 hearts left in the bag. So 10 over 49 would be my chance. And you just keep reasoning that way until you get through it all. That's not the answer to part B. That would be the chance of getting your colors in exactly that order specified there in the shaded region, okay? And you want the chance of getting 3 whites, 2 tans, 1 pink, 1 yellow, and 2 greens in any way, in any order. So you would actually have to multiply this chance by the number of ways to spell a word with those letters if you wanted to correct your answer. Number 20 in section 1.4. Okay, so this is where the 2 people are shooting at targets, and each person has their own chance of hitting the target, P1 and P2. Their shots are independent of each other. Could you choose hitting probabilities P1 and P2 so that the probability that neither hit is equal to the probability that exactly one of them hits, and that's equal to the probability that both of them hit? Could all 3 of those probabilities be the same? Well, the way I'm going to approach that is to first write out each of the probabilities in terms of P1 and P2. Chance of no hits is the chance they both miss. Independent says multiply the miss probabilities together. Chance of 1 hit. Well, person 1 could hit and person 2 could miss, or person 1 could miss and person 2 could hit. Chance of 2 hits, P1 times P2. Okay, now if all those 3 probabilities are equal, then this probability has to be this probability, among other things, leading to this equation number 1 here. And I work with number 1 a little bit. I multiply out the left-hand side and I simplify what I can. I get this little equation 1 prime here. the two probabilities have to sum up to 1. Okay. Also, this probability has to be equal to this probability, leading to equation 2 here. And again, I just multiply out. On the left-hand side, I get this expression. And I gather together my P1s and P2s, and I've got 3 of them on one side. And on the other side, I still have just a P1 and a P2. But by equation 1 prime, that's a 1. So now I'm down to this equation. And P2 is 1 minus P1 because P2 and P1 have to sum to 1. And so I've got an equation that has just one of the P's in it. And I gradually work it up to the standard form for a quadratic equation involving this unknown P1. And I see like, well, okay, could there be a solution here? Well, the quadratic formula says the solution would be this. But when I work that out, there's a minus that I'm trying to take the square root of. P1 would have to be a non-real number. It would have to be a complex number that's not a real number. And in fact, so would P2 as well. And so they're not even real. They're not real numbers. They certainly are not real numbers between 0 and 1. So they can't be probabilities. So there are no possible values for P1 and P2 that allow all 3 hit probabilities to be the same. So that's one way to solve the problem, is to kind of come down to a quadratic equation like that. Other people offered some other ways where they found that like a certain quantity involving P1 and P2 had to be one thing, and they reasoned a little bit more, and they saw that same quantity had to be a separate other thing, and so that was impossible. There's lots of ways to come to a contradiction. In section 5, number 8, I thought it would be good to just record one solution to one of these Bayes' theorem problems. So this is the one where there's 4 different brands of some kind of tablet, brand 1, brand 2, brand 3, brand 4. And each of those brands, the tablet made by that brand has a certain chance that it needs repair. And you get a tablet, and you don't know what brand it's from, but you find it needs repair. So could you find like the probability, given that it needs repair, that it's a brand 1 tablet? And the probability, given that it needs repair, that it's a brand 2 tablet, and so on for the other 2 brands. Well, I'm just going to write down a solution for the probability that it's brand 1 if it needs repair, okay? And rather than just whoop out Bayes' theorem straight up, I'll take you to Bayes' theorem step by step, because it's so important to just remember, so important to keep in mind, why things are like they are, rather than just memorizing more and more theorems. So this is a conditional probability, so by definition it's this. The top is the probability of an and, so I could use the multiplication rule for intersection of events, but use it like that, because I actually will be able to know the probability of repair given that it's B1. I know that. That was 10% said in the problem. And I also know the probability that it comes from B1, 40% of the tablets that you get are from B1. So that'll be a 0.4. Now, how about that probability that it needs repair? For that, we can use the conditioning principle. There are these 4 events, B1, B2, B3, B4, that the tablet is from each of the 4 brands. Those events are disjoint. No 2 of them can happen together. And they are exhaustive. They union up to the sample space. So you can condition on them to find the probability of repair. So using the conditioning principle, the probability of repair is the sum of those 4 conditional probabilities times the absolute probabilities for the BIs. And when we write out everything we know about those probabilities, then we get 63.5% chance. So before you look into the tablet and see whether or not it needs repair, you would think 40% chance that it comes from brand 1. But after you see it needs repair, that chance ups in your mind to 63.5%. Wonderful, Bayes' theorem. Okay, that's all I've got for selected solutions. Let me get you back to your regular day. See you later.